Alright, recursive sequences. We're going to use explicit rules, which we've been using over and over and over again, just to show the difference between an explicit rule and a recursive rule. So to get started, to find the first 5 terms, to find a sub 1, we plug in 1. 11 minus 2 times 1. To find a sub 2, 11 minus 2 times 2, and a sub 3, 11 minus 2 times 3. So here we get 11 minus 2, 9, a sub 2, 11 minus 4, which is 7, minus 6, which is 5, and so the first 5 terms are going to be 9, 7, 5, 3, 1. You guys notice the pattern of it going down by 2, and also recognize that this is our common difference. That's our D in our equation, and so it's going to be going down. Each term is 2 less than the previous, or however you want to say it. For this next one, a sub 1, 48 times 1/2 to the n minus 1. And if you want to remember that this kind of looks like, well, it's an exponential function, and this 1/2 is going to be our r. And so if we find, so it's a geometric sequence. So 1/2 to the 0 is 48. A sub 2, 48 times 1/2 to the first, 24. And so that's 48 1/2 squared, which is 1/4 of 48, which is 12. And so up here it was 9/7, so we have 48, 24, 12, half of 12 is 6, half of 6 is 3, and so on. Each term is half of the previous term. So, these were all explicit rules, meaning that they've been nth term equations, we've called them as well, meaning that you can plug in 1, 2, 3, 4, 5 to get the first, second, third, fourth, fifth term. So now we're going to talk about a recursive rule. With the recursive rule, our description up here is exactly what the recursive rule is going to require. We described 9, 7, 5, 3, 1 as each term is 2 less than the previous. However, that doesn't tell you where it starts. So we would add to our description here, starting at 9, and then each term, and starting at 48, things like that. So what a recursive rule requires is where to begin. You need to know the first term, and then a rule of how to get the next term. All of this, the trickiest part about this is going to be notation. So a sub n, remember, is any term. And then a sub n minus 1 is going to represent the previous term. Here's what I mean. If n was 5, 5 minus 1 would be 4. If it was 6, 6 minus 1 would be 5. So any way you cut it, n minus 1 is going to represent the previous term. So here's what they look like. A sub 1 equals 3, so that's the start. Where to begin? That's your first term. Sometimes it gives you your 0. It doesn't matter all that much. A sub n equals. So to find a sub 2, I'm going to use the previous term, a sub 2 minus 1 plus 5. A sub 2 equals a sub 1 plus 5. A sub 1 I know, because it's 3. 3 plus 5, so a sub 2 is 8. So the biggest thing you need to know is that a sub n minus 1 is the previous term. And so if you were to describe this in words, you would be fine with this. It's just the notation that gets us in the way. So how to find any term is to use the previous term and add 5. So our sequence is 3, 8, 8 plus 5, 13, 13 plus 5, 18, 18 plus 5, 23. So 3, 8, 13, 18, 23. So what we're going to do now is go backwards and write our recursive sequence. 9, 7, 5, 3, 1. That was our first sequence we had, and we called that an arithmetic. Anytime that you have a common difference, subtract 2 every time. Anytime you have a common difference, it's arithmetic. So the recursive rule, we need a beginning, a sub 1 equals 9. And then a sub n, and how do we get to the next term using the previous term? So we already said subtract 2 every time. So a sub n minus 1, the previous term, minus 2. So in general, you're going to have a sub n equals a sub n minus 1 plus whatever your d is. In our case, d was negative 2, and so we added a negative 2. This next one, we multiplied by 1/2 every time. Your r value was 1/2. Because it was multiplying by something, that made it a geometric sequence. And our recursive rule, well, first we need our starting point. And then we're going to use our previous term, a sub n minus 1. And we're going to multiply that previous term by 1/2. And so 1/2 like that. Or you could write it as a sub n over 2. And that would also work. So in general, a sub n for a geometric sequence is going to be 1/2, or sorry, r, whatever r is, times a sub n minus 1. Of course, for both of these, you're going to need your first number of the sequence as well. So let's try writing a couple of these. Write the next 5 terms of the sequence. So again, remember that this is the previous term. So to find a sub 2, you're going to be negative 2 plus 3. A sub 3. This is 1, so you get 1 plus 3, which is 4. A sub 4, 4 plus 3, 7, so on and so forth. This is your D. And so you get negative 2, 1, 4, 7, 10, and 13 would be the next 5 terms. This is the first term. Alright, so this one's a little bit different. A sub n minus 1 is still your previous term. But now we've thrown in a sub n minus 2. And so let's try to find a sub 3 and just plug in for n. If n is 3, a sub 3 minus 1 plus a sub 3 minus 2. So that's a sub 2 plus a sub 1. So we're going to add 1 plus 1 and get 2. So the third term is 2, and in other words you see that this is the term before 3, and then this is 2 terms before 3. 2 terms prior. So then a sub 4 is going to be 2 plus 1, the third term plus the second term. And the fifth term is going to be the fourth term plus the third term. A sub 6, the fifth term plus the fourth term, 5 plus 3. So this is 5, 4, 4, 3, 3, 2. And so that's 8. So our sequence is 1, 1, 2, 3, 5, 8, and then 5 plus 8, 13, 8 plus 13, and so on and so forth. This is what we call the Fibonacci sequence, and it's pretty cool. Look it up sometime, because there's a lot of patterns in nature and the golden ratio and things like that that come from the Fibonacci sequence. So, writing recursive rules, back to that. So, how do we, things to look for when we're writing recursive rules, think something being added every single time is something being multiplied every single time. So this is arithmetic and geometric.